Hello, I want to talk today about the problem we didn't have time to go over in class, the structure determination problem that was on the class problems, IR and NMR handout. So it's problem number 2. So this is the structural information. I think you got it all there. So that was one that was handed out in class. It's also online. So what I want to do is just work through this and go through how I would solve this problem, just to give you an idea of the sort of strategy and thinking that I want you to use when you're doing similar problems. So I've written on the board what's on the back of this sheet, which is the strategy that we're going to use to solve these problems. And I want to just work through it with you. All right, so we've got the table up on the board. We have the spectral information in front of us. And so let's just roll through this and see how we do. So as I've said before, you can get a lot of information out of the molecular formula. So we have C8H11N. So let's determine degrees of unsaturation, right? So let's do that. We know that we have to get rid of the N and turn that into something that's a hydrocarbon. So when we subtract N, we add CH. So this is really C9H12, right? The saturated version of C9. So saturated is going to be C9H20. Because it's CnH2n plus 2, so 2 times 9 gives you 18 plus 2 is 20. So then you end up with 20 minus 12 over 2, and that gives you 4. Okay? So we have 4 degrees of unsaturation. We've said in class that if you have 4 degrees of unsaturation, more than likely you have a benzene ring. Right? So let's think benzene. Right? If we are thinking benzene, that would mean that we would have used up 6 of the 8 carbons. So if it's benzene, and then we have 2 other carbons, and we have a nitrogen. We have no degrees of unsaturation, so we know that this nitrogen must be an amine. It can't be part of an amide. It's got to be part of an amine. And so hopefully right now you're thinking, is this amine an NH or an NH2 type amine? So is it a primary or secondary amine, or is it a tertiary amine? And that's something that we can answer pretty easily by looking at the IR and the NMR. All right, so before looking at any of the spectra, we've got this information laid out. All right, so let's go to the IR. You can look at the IR. I have the peaks laid out here. If you look at the spectra reference sheet for IR, you can see that these two are in the amine region, and it looks like a double peak. So this is probably an RNH2, right? A double peak for a primary amine, right? So that answers this question, right? So primary amine. So we're really starting to narrow the structure down right now. If it's a primary amine, NH2, and a benzene ring, then we just have 2 other carbons to place and we're done. 3023, that makes sense that this is CsP2 to H bond, right? We know we're going to have some carbon-hydrogen bonds from the benzene ring, so that makes sense. We have 2 other carbons that are saturated, so those are going to be CsP3 to H, so it makes sense that we have that peak as well, just below 3000. And we know in the benzene ring we have carbon-carbon double bonds, so that 1622 peak is a carbon-carbon double bond, right? And it's really important when you're analyzing the IR, focus on the bonds that give rise to the peaks, because it's all about those bonds interacting with IR light. So every time you go through the IR, you should focus on the bonds giving rise to the peaks. All right, so now we need to verify functional groups, and I think this is really important. Right, so if we have a benzene ring, we should be able to look really quickly in the carbon-13 and proton NMR and figure out, yeah, we definitely do have a benzene, okay? So if we're looking at the C13, we're looking for peaks that are going to be between, so what does our sheet say? Our sheet says 120 to 160, right? And you'll note that I've got the peaks listed out here. Right, there's our benzene ring. All right, and they're a little bit outside of this range, 115, 119. So again, know that the ranges can expand a little bit but we definitely have those peaks in the C13. And then for the proton NMR, we're looking for peaks that are between 6.5 and 9. And you'll see that we have right here 7.2 to 6.6. So we have carbon and proton peaks that are consistent with the benzene ring. So we definitely have a benzene, which is great, right? That makes things very, very good as far as our structure determination goes. We also said that we have some sort of RNH2 group, a primary amine. And primary amine, it has protons on it, so we can look for that peak in the proton NMR. And one thing that's important to remember when we have NH or OH protons, those protons will always show up as a broad singlet, right? So we're looking for a broad singlet, right? And that's going to be true for OH, NH, or NH2. So protons on those electronegative elements always show up as broad singlets, and they don't participate in splitting. Right? So they're not split by neighboring protons, and they do not split neighboring protons. Right? And this is, I think, an interesting knowledge forum question. Why? Why don't they participate in splitting? So that's something I'd encourage you to think about. But regardless, for right now, we're looking for a broad singlet. Right? And if we go down here, we can see we have this broad singlet at 3.5. Right? So we've just verified we have a primary amine and we have a benzene ring. Excellent. Right? Carbon 13, we've already said those 6 peaks are from benzene, right? And then we have these 2 other peaks that are the C2 that we mentioned up there. The really important thing at this point is to recognize that we have no symmetry, right? We have 8 peaks. There's no symmetry. All right, that's important. Because remember, if we have fewer peaks than a number of carbons in our molecular formula, that means there's some symmetry involved in the molecule. So for this molecule, we don't have any symmetry. All right? So we've learned a lot without even looking very much at the proton NMR. Now to figure out what's going on with our structural fragments, we need to look more deeply at the proton NMR. Right? And one other question that I hope we have here, and let's see if we can answer this quickly, is what is the substitution pattern for benzene? Right? Another way to ask this is how many protons